here is just the line integral of E times S. E is constant, so the voltage difference is V times S. Okay. Now suppose I have an electron here minus E. I put it just right at time equal to 0. I put it next to the left plate. Okay? Left plate, the right plate. So experience an electric field coming from the capacitor plate, right? So because the electron has a minus charge, then it will experience a Coulomb force in the x direction. Okay, and the force is the force on the electron. F is just E times E in the x direction, carried only in that direction. Okay, and because there's a force, there's an acceleration from Newton's law. Right? Mx double dot is equal to F in this case is equal to E times E. Okay, so x double dot is equal to, okay, this is the acceleration. And suppose the electron is stationary at time equal to 0, then the time dependence of the velocity as a function of time is then equal to, you should be familiar with this by now from physics 7a, times time. And then the position as a function of time is given by 1/2 E over m times t squared. Okay? So at some point at time Tf in final, the electron reaches the other plate, right? And that happened here is final is equal to, just looking at the last equation here. Right? Substituting S to X, I get T final is equal to, my note here, square root of 2s times m divided by, okay, where m here is the mass of electron of minus E, and it's equal to 9.1 times 10 to the minus 31 kilogram. Okay, any question? And what is the velocity of the electron when it reaches the right plate?
What's that time?
Sorry? Yeah. You can either substitute the time Tf into this equation, or there is an easier way, right? You have conservation of energy. And so 1/2 mp squared has to be equal to the potential energy loss, right? That's the electron goes from this plate to that plate, okay? And that would be equal to E times V, right? Okay? I'm very cavalier here with all the sign, but you know, at the end of the day, the physics should be clear. So this should be E times E and S. So V final goes as 2E S over M. Okay, plot is clear, plotting that x dot T is function of time is linear like that. And then this is x is function of time. Final. This is quadratic. Here. This is S. Okay, so very straightforward. Anything to go for? No?
Wait, what's EV?
Sorry?
Where does the EV, what happens to
This is the potential energy change.
Oh, okay, so that's
Right.
part of the
So
competition.
this part of basically what you have is conservation of energy. the changes in potential energy
Oh, the U.
give you kinetic energy.
Okay.
So you accelerate the electron from here. It goes from high potential energy to low potential energy. Remember, electron is a minus sign.
Right.
Right? Even though this is higher potential, this is lower potential. But because this is an electron, then the potential energy is higher on the left, lower on the right. Right? Okay? So let's do something really this is an interesting example. Remember from problem, what was the problem that you have to do in this homework? Problem 37, right? Okay, so you have, if you recall this problem, if I have a charge minus E over here, and if this distance is x, and this distance is s, right? There's an image charge here, Q1, there's another image charge here, or let's call it QL, another image charge QR. Okay? And then you solve this in your homework, you'll find that QL over QR is going to be equal to S minus X, or in the homework it's actually called B, but I want to use X in this case here, divided by X, okay? And also you know that QL plus QR, okay, has to be equal to plus E, right? Plus E, right? Okay? So when you solve for these two equations, you'll get that QL is going to be equal to E times 1 minus X S. QL, no, QR is going to be E times X. So what happened is as the electron moves from the left plate to the right, right? There's a positive image charge to the left plate, right? It's also moving in that direction correspondingly, right? And the quantity is given by that. And there's another image charge QR, right? And as the electron moves towards the right, it's getting closer and closer, and the magnitude is given by that. Okay. So let's see. Let's formalize that. Let me erase this. Since you did the lab last Wednesday, I'm going to have no form in introducing battery here, right? So in this case here, recall that I put the delta T over there, right? So if I introduce, this is the lab that you have, in your experiment, right? And this is the cycle battery, right? It is your voltage supply that you have in your lab, right? So in this case here, this is the left plate, this is the right plate, an electron moving that way, right? Okay. Then because of x is a function of time here, right? Then what you have is a QL is given by that, and QL dot is just equal to minus E x dot over S, and QR dot. You guys know what dot means, right? It's the rate of change with respect to time, right? It's given by E x dot S, right? So QL dot is equal to minus Q dot. Okay? So this is accurate. QL, this is time. No, this is time. I want to plug with respect to time. Let's do it later. substitute the expression for velocity, x dot as a function of time is for what's that? Is equal to et over m times t. Then from here, I get ql dot is equal to, I don't want to do all the algebra, it's going to be equal to minus e squared e over m times t. Okay, and then qr dot is just the negative of that, is plus e squared e over m. Okay. I'm missing something. I'm missing s here. Okay, so if I look as a function of time, right, on QL, it started high, right, because at the beginning here, then immediately as the electron leaves the left plate, you have a positive image charge on that side that diminishes over time, right? So QL dot looks like this, right? It started as plus E. And QR started at 0, goes linearly in time. This is defined. So as you see, the image charge, right, on the left, the image charge drops. Right? The amount actually decreases in time. And then the image charge on the right, QR, decreases, right? Okay. So what happened here, the fact that you maintain the potential difference V here, this is V equal to 0, this is V equal to V, equal to V times S, right? What happened is that you have, so everything is positive here, right? This is a Q plus QL is positive, it is decreasing, so you have current flow or charge flow going from this plate down. So as your electron move from the left plate to the right, at the same time, you need to close the circuit. Positive charge will flow from the left plate through the wire here, through your battery, to the right plate, to meet the electron. And at the end of the day, you have conservation of charge.
But if the battery wasn't there, it wouldn't be a conservation?
Well, suppose I want to maintain a potential difference. Right?
Mm-hmm.
I mean, you can analyze this differently, and then things will be slightly different.
Wait, because the electron is moving, positive charge flows in around?
No. Yeah, because the electron moves from the left plate to the right plate.
Yeah.
Right. If I'm just analyzing the image charges,
Yeah.
you see that the image charge on the left drops.
Oh yeah, when you're
Right.
like where the...
And this is exactly from problem 337, except what you did, what you solved, was a static problem. I wanted to do this for the midterm. Right? It's like a cool problem for the midterm, right? But I said, no, I think it's a better way to describe it this way. So QL drops, and QR increases. Right? So what you have is charging, charge. Some of the charge flows from the left plate through the wire, through the battery, into the right plate. Right? To meet the electron.
Yeah.
Right? At the end of the day, you must have conservation of charge.
This is a way to like view it, right? Like a way to know, to think of conservation of energy.
I mean, the standard way to think about it is that, I mean, sure, this is the way to think about it, right? You have an electron flowing that way, right? This is what you learn in college textbook, right? And the electron will just travel through the wire and goes downwards. I mean, that's also a good picture. Right? But what I'm trying to tell you is that immediately as the electron leaves the surface of the left plate, you already get a current flowing.
For the image charge?
from the image charge.
But I thought they were real.
Yes, yes.
Yeah. Well, which way is the?
So the electron flow this
So
way,
how is it
right? The
going?
electron flow that way,
Yeah.
right? And it's flowing that way. The image charge flow this way. Yeah.
An actual current is generated.
It's an actual current is generated.
That's so weird.
Okay. An actual positive charge move away from the left plate
Mm.
onto the right plate. Giving rise to this, like QL drops and QR goes up. The sum is always constant. Right? This is linear, this is always linear. And then QL plus QR is always equal to the same. Okay? So with that in mind, I want to move on. This is actually an example given in Purcell, so you can analyze it this way. So this problem is called a vacuum diode. So way back when there is no semiconductor diode, this is what you use to create current flowing only in one direction, right? So this is the setup. What you have is again parallel plate, some voltage difference, okay? And this is just metal. And this is a special material, it's some alloy that has a very low work function. So when you heat it up, right? So if you heat this up to temperature T, what you have is 0, this is B, electric field going that way. When you heat it up, electrons start to leave the coil. At low energy. It's called thermionic. I don't know what the Purcell called it, thermionic current or emission. So what happened is that you suddenly acquire some concentration of electron over here, free from the metal because of the temperature. Okay? And then it gets accelerated towards the right way. And it doesn't work the other way around. Right? So electron can only flow that way. Right? Meaning that there's a current flows this way. Right? And things cannot flow the other way around. I don't know if you study electronics in high school or not. That's a definition of a diode, right? Diode basically allows the symbol for a diode, right? It allows current to flow that way, but it doesn't allow current to flow in the other way. Right? And this is how it was done in the past, way back using vacuum technology, like from 1920s or something.
So why is that one different than that one? That cap doesn't allow transfer the other direction?
Yes, this is the same idea here. This is exactly the analysis of a vacuum diode.
But you said that no charge can travel.
Right. So current can only flow this way, right? See this current? The current here flows from the left plate to the right plate to meet the electron. The electron flows this way.
I thought you said that the electron also passes through.
Yeah. Right.
Is it happening there too?
Correct. Yeah, it's happening here. In fact, it's always electron that move, right? The positive. In this analysis for electrostatic analysis of electrostatic, we pretend that plus charges move, minus charges move. But say in most solid material, it's only the electron that move. Right? So when I say that positive charge move, actually is a negative charge that moves the other way around.
So can you just think of it as the electron pushes charge away from the other plate, back to the first plate?
The electron, yes, is pushed, well,
Like it pushes electrons off of the right plate back onto the left plate as it moves to the right?
yeah, you can think of it that way. I mean, you have to be careful here, right? The electron is a if I instead of analyzing it with the voltage, source, right, which is makes things more transparent. I can also introduce plus charges here, right? Plus sigma, minus sigma, right? And I think things got slightly more complicated. If you want to analyze it this way, I don't want to do it around the class right now. But what happened is the electron get attracted to all the positive charges, right, and get repelled from the negative charges. Right? But it's doing that, right? I mean, I don't know how to analyze this, right? Because the electron gets repelled that way. Somehow there's an image charge that also moves this way around. I don't know. But at the end of the day, the analysis holds. Right? I think this is the clearest way to think about it as well as this is how I think about it. But the vacuum diode doesn't allow electron to flow in the other direction, right? Because you only have a special material on the left plate. Right? The thermionic emission comes only from the left plate, goes to the right. Right? You don't have any thermionic emission from the right plate, right? So current cannot flow, electron cannot flow the other way around. Okay, is that clear so far? So this is going to be the prelude to a discussion on so now, current. So let's first define by current density. Usually for J, okay, is equal to the amount of charge flowing per unit area per unit time. Okay. So this is very similar to your study of hydrodynamics or hydromechanics in 7A, right? So in this case here, then J is usually given by in your case in the past, it was mass density, but in this case what you have is a number density times the charge of the carrier, right? So you have a density of carrier, you have the charge of the carrier, right, times the average velocity, right? This is the current density. Okay, so in particular, if I have a current density flowing that way, right, and I have an area dA, okay, then the volume of charges in time t, right, then if you can see, if just for simplicity, let's think of all the carrier move at a particular velocity, right, a particular speed, then everything that's in this volume with a linear dimension of v delta t will pass through TA, right? And that amount, that's called the flux, is equal to times the density, right? Density of the carrier, right? But multiplied by the charge of the carrier, in this case it's always E, right? Which is the density there times V delta T times A, right? Okay. And this is going to be equal to, this is how you define J, the current density, and the
Is this V velocity?
V is a velocity V. It's an average velocity. Okay. So, and a flux. Seems to get confusing with the units. A current is just a flux, right? So if I have a current density like that, J, right, area dA, then the flux, or in electrostatic, is current. It's just J dotted dA, right? And you know what this is dotted, right? We can do the same analysis here, right? Sorry? Right, so if I have a J going like that, normally dA, right, then the amount of charge that flow through this surface here is J times dA. Now I can see this drawing in such a way that now this is slanted here, so the dA is a component in that direction, right? Then because here, just like in the case of hydrokinematics, the density is not compressible, right? So what flows in must flow out, right? So J that flows in must flow out, right? Then, but this area is larger, but the projection is actually dA cosine theta, right? This angle is theta, right? So J dA on the left is equal to J relative to dA here on the right. Okay? And this is the amount of current that flow through any surface, right? So in particular, if I have, some field of current density, right? And if I draw a surface S, then the current that passes through the surface, current is just flux. It's just an integral to the surface J, surface S, J dot dt. Okay. I want to erase this part. I will erase the discussion on the application here. I will get back to this at some point. This can make a very interesting homework problem, over a closed surface, if I have a closed surface, right? If I integrate over all the fluxes through the surface, right? If I integral, okay, so basically I'm calculating the current that passed through the surface from the inside, right? Then this has to be equal to the rate of change of Q inside, right? Just by conservation of charge. This is no more than a statement of conservation of charge. Right? Charges cannot disappear, right? So this becomes an integral minus ddt, and charge inside is the integral over the volume of density rho, right? Times dT. Remember, rho is always defined as charge density from now on. Right? N is the number density. Small n, lowercase n is the number density. Okay? Conservation of charge. But you also know that an expression, a flux over a closed surface can be expressed as an integral over a volume of the divergence. Right? We did this for electric field. Right? And I did the proof of that either in discussion or in lecture. So the left-hand side is just equal to the divergence of J. Right? The left-hand side is still the same, minus ddt over dt. And this is true for any distribution of current density. It's true for any volume that you draw, or any closed surface that you draw. This is always true. Right? Therefore, it must be identically true that as a consequence of a conservation of charge, that the divergence of J, right, or sometimes written as like this, is equal to minus d rho. Okay? A lot of the time is actually written as all of it on the left hand side, gradient J plus dt equal to 0. This is called, in electrostatic or in electromagnetism, is called actually conservation of charge, but it's also called continuity equation. I don't know what's called this, but it's called this. Continue the equation, and it's just a consequence of conservation of charge. Question? I'm going through this very fast, but this also is straightforward from your understanding of hydrodynamics.
For the integral one, is this one charge is changing when there's a change of?
Say it again.
When there's a change of like the charge, or?
Yes. There is so what flows basically this statement here, or this statement, right? What flows out of a closed surface, right, has to be equal to the rate of change of the charge inside, right? So if charges are leaving this volume, then the total inside has to drop. That's basically what this says, right? Or this is the and then this is just the exact same statement. That there is an integral statement, right? And I'm just converting the integral statement here into a differential statement, right? This is completely identical by analysis of vector calculus. Okay.
Is it just sometimes easier to solve via differentials rather
yes,
than integral?
depending on the problem of interest.
Okay.
But I mean, you can analyze it both ways, right? Like say Maxwell many years ago, right? And everything was expressed in terms of an integral calculus. There was, nothing was expressed in the differential calculus. And you can still do it. Question so far? Okay. Now. Remember that and remember this. Current is just an integral of J dA over any surface. Okay. In particular, for most problem of interest in electronics, what you have often is a steady state problem. So things are changing, things are moving, just like a river, right? But the solution is steady. Nothing really changes in time on average. So in that case, d rho is equal to 0, right? So this equation then becomes the divergence of J is equal to 0. That's the steady state. Okay. So let's go back to the problem of the vacuum diode. In the case of a vacuum diode here, okay, you can also think of a concept of current here. It's just mostly for bookkeeping, right? One electron vacuum diode. Then the current is just, or the current density, right? Current density is equal to, it's just one electron, right? One electron, right? Per unit area, per unit volume, right? And the volume here is at an area A, and separation S, right? Divided by the volume, area S, right, times velocity. So this is E, V, or Ex dot. Now, V is velocity is just x dot, right? Over A times S. Okay? So the current through the capacitor, right? This is just a capacitor, by the way, right? This is special time. then the current is just J times the area, right? So current is just E x dot over A. No, the A cancel, right? Over S. Okay. Okay. And then if you remember, x dot, we solved with this, is E times E over M times E, right? This is just Newton's law. I substitute this into this equation. Then I have current is equal to E squared E over MS minus E.